Welcome, everyone. My name is Hongseok Namkoong, and I'm going to talk about how we can do causal inference that's robust to unanticipated covariate shift. This is based on a joint work with Sookyo Jeong. So, as we all know, these large-scale prediction models have been very successful, driving a lot of progress in computer vision and natural language processing. And in order for us to leverage these tools to make important real-world decisions that are reliable and effective, we need to uncover causal relationships rather than read off of spurious correlations. And these problems, they don't fit into a typical prediction setting because the questions you're interested in answering are of a counterfactual nature. Would this patient have gotten better without taking this drug? And if the doctors were giving the drug to mostly people who would have gotten better regardless, then a naive prediction model would end up overestimating the treatment effect. So to concretely write down the counterfactual states of the world, we're going to use the potential outcomes framework. And this allows us to write down the outcomes that would have been had we used a different treatment option. We're going to focus on binary treatments today and denote by Z the treatment assignments. Z equals to 1 is the treated units and 0 is the control units. And we're going to let Y1 and Y0 be the potential outcomes corresponding to these treatment options. And again, the problem here is that we don't get to observe the counterfactual, so we only observe Y, the potential outcome, at the assigned treatment. So given this data, the standard thing to do is to estimate the average treatment effect, which is the expectation of the difference between these potential outcomes. So evaluation of clinical treatments and policy programs and tech products, they're all universally based on statistical inference of the ATE. And this is an average of the conditional average treatment effect, which is just the conditional expectation of the difference between these potential outcomes given the observed covariates. And this is a key nuisance parameter that you may want to use ML methods to predict. Now, again, the ATE is the average of the Kate under the data generating distribution for the covariates, which we're going to denote by P sub x today. Now, the ATE is only the right measure of treatment effect if the underlying data generating distribution is actually representative of the overall population of interest. However, data collection is often quite messy, and it's done on a handful of geospatial locations at a particular point in time. So to illustrate this here, let's consider an experiment in Oregon in 2008, where folks were interested in whether having access to insurance translated to more emergency department visits. Now, if we want to use the results of this experiment to inform policy decisions nationally, or if you want to have this policy to have an enduring effect throughout time, then we really need to make sure that this treatment is effective for all subpopulations. And as we see in this plot, one challenge is that the demographic proportions of even these basic characteristics can vary quite significantly per state, and even in the same state through time, varying up to tenfold in the span of only 10 years. And this mismatch between the data generating distribution and the overall population of interest, this gap persists even for carefully designed randomized trials. So here we have a plot from Tipton et al.'s great paper that analyzed the covariate distributions of 34 different school studies that were funded by the Institute of Education from 2011 to 2015. And here we see that there's a salient gap between a typical study population and that of the national school population, in that the studies were often conducted in a large school district. So 73% of school districts in the country only have 1 to 5 schools. But in the study population, these small school districts were only represented 26% of the time. Another really serious issue is that the data collection process is often extremely biased, and minorities are really not represented in typical studies. So for example, from 1993 to 2013, 98% of all studies in respiratory diseases didn't report any inclusion of minority subjects. And this is despite the fact that Blacks are more likely to suffer from these diseases. And out of more than 10,000 cancer trials that was funded by the National Cancer Institute, less than 5% of the participants were non-white. And this is especially problematic when the treatment effect is quite heterogeneous, varying across covariates. And this is true in a lot of medical applications. And as a result, even the large-scale clinical trials, they tend to lose validity in face of covariate shift. So one prominent example is the Accord and Sprint trials, which studied the effects of treatments to lower blood pressure on cardiovascular disease. And both trials had large sample sizes between 5,000 to 10,000. But the top-line conclusions for these two studies had the opposite sign. And the mechanism behind this difference could not be explained by experts even ex post. Now, a true believer in AI might say, oh, let's use a learning algorithm to predict the conditional average treatment effect may maybe personalize the treatments. But we all know that these learning algorithms can be very biased when the data inherits the social institutes and the racial divide in society. And of course, there's been an explosion of works in machine learning that's identified a number of these failures. And we see that resulting estimates of the Kate, they often end up with underpowered decisions and they're very unstable. Now, a standard, simpler setup is to use subgroup analysis, which defines a very small number of subgroups to analyze separately. But this is also quite challenging in practice because adversarially affected groups are often determined by a combination of multiple demographic characteristics like race, gender, age, income, and so on. So here, this figure illustrates this difficulty in the Oregon health insurance experiment, where we see that low-income females are unemployed. They actually see a decrease in emergency visits due to access to Medicaid. So there's these quite non-trivial intersectionality in the heterogeneous treatment effects that makes a priori definitions of these subgroups quite difficult. So today we're going to take a new approach and consider an infinite number of subpopulations of a given size, and we're going to measure the treatment effect on the worst of subpopulation. Concretely, I'm going to begin by defining what I mean by a subpopulation. So today I'm going to say that a distribution over the covariates, Q sub x, is a subpopulation if there exists a demographic proportion small a between 0 and 1, and another distribution Qx prime, such that if you mix Qx and Qx prime according to this demographic proportion, then you exactly recover the underlying data generating distribution P sub x. So here, this purple curve is a subpopulation in the sense that if you mix this gray curve with this purple curve, according to the demographic proportion equal to 20%, then you exactly recover the underlying data generating distribution, here depicted in black. So pictorially, here's another example. Here's another example of a subpopulation. Here's another funny looking one. And here's another one. So we're going to consider a whole bunch of different subpopulations. And to ease notation, I'm going to say that a subpopulation Qx is larger than some level alpha, and this level is between 0 and 1, if the demographic proportion corresponding to the subpopulation is larger than this level alpha. So given this notation, we can now define the worst case treatment effect over all subpopulations that are larger than this level alpha. We're going to denote this by the WTE, and this is simply the supremum over all subpopulations that are large enough, and we're taking the average of the Kate according to this subpopulation. So in this definition, implicitly, we're saying that negative treatment effects is the desirable outcome. So we're taking the worst case, which is why we're taking the supremum. But the opposite case is also symmetric, but let's just stick with the supremum case for simplicity today. Okay, so the definition of the WT, it involves an infinite dimensional optimization problem over probability measures. So to make this more tractable, here we have a dual form that's due to Shapiro et al., which shows that the worst case treatment effect is equal to a tail average after some threshold eta, and eta is the dual variable. And the optimal dual variable eta is obtained at the 1 minus alpha quantile of the Kate. And this dual form, it illustrates that the worst case treatment effect cares about people who have really bad treatment effects, in particular larger than the 1 minus alpha quantile of the Kate. And this tail average is also known as the conditional value at risk in operations research and finance, and it's a very popular risk measure. Okay, so we now want to use this dual form to come up with an estimator for the WTE, and we want to use an approach that can utilize flexible learning algorithms for estimating nuisance parameters in the setting. So here, the first nuisance parameter is the outcome model, the conditional expectation of the potential outcome given the observed covariate. And the second standard one is the propensity score, which is the probability that you're going to be treated given the covariate. And lastly, we have a somewhat non-standard threshold function, and this is because we want to estimate tail averages. Okay, now since predictions from ML algorithms can be quite unstable and inaccurate on certain covariate regions, we want to construct an estimator that's insensitive to error in these nuisance estimates. So to do this, we're going to come up with a control variate like augmentation term that has mean 0, but it's going to promote insensitivity to errors in the nuisance estimates. So throughout, we're going to use the standard ignorability assumption, which says that the potential outcomes are independent of the observed treatment assignments given the covariates. Of course, this holds in randomized trials, but this is a real assumption in observational studies. Okay, so under this assumption, we're going to use this augmentation term kappa, and we're going to estimate the WT plus the expectation of this kappa term at the true nuisance parameter. And of course, this mean is 0. So you're not really doing anything. But it turns out that this augmented statistical functional, it satisfies a key orthogonality property compared to the non-augmented version, simply the WTE. So this means that the derivative of this augmented functional with respect to the nuisance parameters is equal to 0 at the true nuisance parameter value. And this is going to allow us to become insensitive again to these errors in the nuisance estimates. Okay, so specifically, we're going to estimate the augmented functional by performing sample splitting. So we're going to fit nuisance parameters using a learning model of your choice on 4/5 of the data, say, and then we're going to evaluate these augmented functionals by using these nuisance parameter estimates on the remaining data, the 1/5 of the data. And by changing the rows of these splits, we're going to get 5 different values, and we can simply average them to get our final estimator. Although you don't really need to understand the details of the augmented terms here, what's worth noting here is that our estimator reduces to the usual augmented inverse probability estimator for the ATE when you set alpha equal to 1. That is, if you're not considering any subpopulations. So you can view our estimator as a generalization of the AIPW under unanticipated covariate shift. Okay, so by virtue of satisfying this key orthogonality property, our estimate of the WT, it can converge at the standard 1/n rates of convergence, even when you can only estimate the nuisance parameters at slower rates. So here we have a central limit theorem for our augmented estimator, and we can also provide a consistent estimator for the asymptotic variance so that we can construct confidence intervals for the WT that has asymptotically exact coverages. So in the proof, roughly speaking, there's an asymptotic expansion for our estimator, and the orthogonality property, it allows us to cancel out the first-order terms that depend on the errors in the nuisance estimates. So previous work in semi-parametric inference, they largely studied linear statistical functionals. But as we saw, the WT is a very nonlinear functional. So to deal with this, our proof is somewhat involved, and it requires a different asymptotic analysis than previous works. Okay, and to complement our methodological results so far, we also give a fundamental hardness result in our paper, which shows that the asymptotic variance of our estimator is actually the optimal thing, the best thing you can ever hope for in any sensible estimator. And this is true in both randomized trials and observational studies. Okay, so to illustrate our method on a data set, let's go back to the Oregon health insurance experiment in 2008. So here, the goal is to evaluate the effect of having access to Medicaid and see whether it allows more emergency department visits for low-income adults. So the 2008 experiment was a precursory study to a federal Medicaid expansion in 2014. And this is a really important policy decision, one that costs $553 billion every year. So here we're going to take the viewpoint of a policymaker between 2008 and 2014 who's contemplating the details of the Medicaid expansion that's going to happen at a national scale. So just to recap here, this plot, it illustrates how the demographic proportions can vary significantly over different states and even temporally in the same state. Okay, so in this plot, we're plotting the estimates of the ATE and the WT for given different values of alpha. And we're also plotting the 95% confidence intervals. So we see that the ATE estimate is positive and statistically significant, and this aligns with findings from previous studies. But these average case results, they fail to be significant, even on subpopulations that comprise of 80% of the data. So here, the WT, it identifies subgroups that are disparately affected by the treatment, and it shows that the average case findings, they don't hold over demographic subgroups, and they're really brittle to subpopulation shifts. So these results, they raise concerns from the policymaker's point of view, and it questions the validity of the average case findings in Oregon. And this is somewhat intuitive in the sense that the direction of the effect of Medicaid and the mechanism through which it happens, it's not immediately clear. Because while access to insurance certainly allows low-income adults to visit the emergency department, it also gives you access to preventive care, which may reduce the need for emergency department visits in the future. So to conclude, here we see that the observed effects of the emergency department usage in Oregon in the year 2008 may not extend to states with different demographic compositions, or even Oregon at a future time point. Okay, to wrap up, we proposed a robust notion of a treatment effect today, and we saw how estimates of the worst-case treatment effect complements the usual top-line estimates of the ATE by guarding against brittle findings that are invalidated by unanticipated covariate shifts. Theoretically, we derived semi-parametric inference results for our estimator and show that it achieves the optimal asymptotic variance. Practically, our approach allows the use of flexible learning methods to estimate these various nuisance parameters, and it uses them conservatively so that when it finds a non-zero treatment effect, the treatment remains effective across all subpopulations of a given size alpha. So we've provided a framework for analyzing the sensitivity of a study's findings to unanticipated covariate shift. Thanks a lot, and I'd be happy to answer any questions.